Okay, so good day everyone. So today we will be discussing our last topic for power plant. That would be your solar power plant. Okay, so solar power plant is a facility that converts sunlight into electricity. Okay, so we have two types actually. That would be photovoltaic or the solar panels that we are using today, or concentrated solar power huh, to generate electricity. So again, that is just minimal uh, computations for your solar power plant. So let's say that this would be our sun. So we have here a solar flatbed collector. So when you say a solar flatbed collector, that is the one that collects, no? Or siya ang collect all the energy from the sun. Okay, so that is your solar flatbed collector. Then we have here our water. No? Water. Okay, that would be our water. So the solar energy received at the Earth's surface, that would be the heat from the sun, okay, or Q of the sun, would be equal to the Q absorbed by the water. Okay, this would be our water going in. Okay, this is water going in, and this is your water going out. Plus the potential energy of the water. That is because there is a change in height, no, in our flatbed collector. So this change in height contributes to our potential energy. Di ba the formula for your potential energy, that would be mgh. And plus the losses on our solar power plant. So that's it. If the Q of the sun is not given, so we are using 1353 watts per square meter. Okay? If it is not given, but usually in our problems, it is given. Okay? So let's try this problem. A solar collecting panel, 20 square meter in area, received solar energy at the rate of 750 watts per square meter. So the Q of the sun is given. So let's go back with our formula. The Q of the sun would be equal to the Q of the water plus potential energy plus Q losses. So the Q of the sun, that would be 750 watts per square meter. Since naka per square meter siya, so it means we will multiply our area of the collecting panel. That would be 20 square meter. Equals your QW, no? Your QW would be MCP delta T because that is the heat absorbed by the water. Okay? Because that water will be used later on for heating purposes, no? Or for other systems that requires generation of electricity, no? In some places. So that would be MCP delta T. So again, I'll just put it here, your QW, that is MCP delta T. Your potential energy, that would be MGH. And your Q losses, that would be percent loss multiplied to the Q of the sun. Okay, so those are your formulas. So your Q of the water, okay, you are given here the mass of the water, that is 0.05 kilograms per second, multiplied to CP. Take note, since naka-watts kita, dapat ang CP is also in joules. So it means instead of 4.1868, that would be 4186.8 joules per kilogram Kelvin. Then our change in temperature, okay? So the water enters at 15 degrees Celsius. We are to find the temperature of the water leaving. So that is the final temperature minus the 15 degrees Celsius plus no potential energy of the water, that is 0.05 kilograms per second, multiplied to G, which is 9.81 meters per second squared, and the change in height, which is 2 meters. Okay? Plus Q losses, that is 35%. No? So it means 35% of your Q of the sun. So we first compute our Q of the sun here, that is 750, multiplied to 20, that would be 15,000 watts. So we put it here. Then what we will need to do is shift solve for the final temperature. Okay? So 750 times 20 equals 0.05 multiplied to 4186.8 multiplied to the final temperature minus 15 plus 0.05 multiplied to 9.81 multiplied to 2, which is the height, plus 35% of your 15,000. Shift solve. Our temperature of the water leaving is 61.57 degrees Celsius. So that is our final answer. Okay. So next, the sun generates an average of 2 kilowatts per square meter. So again, given our Q of the sun, so that would be 2 kilowatts. So it means 2,000 watts per square meter. But what is the area? That would be 1.5 square meter. Okay. Then Q of the water, that would be 40 M CP of water. Then delta T. Okay, so we are to require the temperature rise. So it means the required here is delta T. Okay, next. Let's check if there is a change in height. So wala, no? There is no given height. So it means potential energy is 0. Next. Are there any Q losses? So wala, no? So it means it is also 0. So what do we need to find now is the mass of water, which is, ang given here is the volume flow rate. Okay? Given ang volume, that is 40 liters per hour. So since given ang volume, that is 40 liters per hour, we multiply that one to, okay, we will convert no, our volume into mass. Okay, so it means we will use our density. So pila ba ang density sang water in terms of kilograms per liter? The density of water, that is 1 kilogram per liter. Okay, so again, the density of water is 1 kilogram per liter. So that would be 1 kilogram per liter. Okay, we need to convert the hour into seconds. So 1 hour, that would be 3,600 seconds. So the final answer would be 40 multiplied to 1 over 3,600. So we have 0.0111 kilograms per second. So we will input it here in our mass. That would be 2,000 watts per square meter multiplied to 1.5 square meter equals 0.0111 kilograms per second multiplied to 4186.8 joules per kilogram Kelvin multiplied to delta T. So your delta T would be okay, shift solve. That would be 64.55 degrees Celsius. So that is our answer.